Hello, I'm Rajagomati. I will be presenting my literature survey on the topic of ultra-low power processing for wearable and implantable medical devices. As it can be seen in this figure on the right, these wearable devices are currently used in several sectors for many different applications. Wearable medical devices are miniaturized intuitive devices that can be integrated with our accessories or clothing, or even can be implanted under an individual's skin. Now, why do we need low power processing for these? Because these are very small devices, and so we cannot really accommodate large batteries in them. Despite this, these devices still need to run for long periods of time without any performance degradation, while still maintaining its small form factor. To do so, we need to reduce the huge power consumption that happens during signal processing. The type of microcontroller that we use, the way signals are received and processed, the bandwidth within which data gets transmitted, the time taken to execute a task, and certain computation operations, all of these contribute towards power consumption. In the upcoming slides, we will look at some of the power optimization techniques. Initially, the patient activities are obtained in the form of physiological signals from sensors such as accelerometers, gyroscopes, and so on. Then these analog signals are digitized using the analog to digital converter, after which the digitized signals are made to pass through the granular decision-making module. This decision-making module, in combination with a low-power microcontroller, saves significant amount of power. In this module, the signals undergo preliminary processing through a set of special purpose functional units called screen blocks. After this preliminary processing, the resulting signals are said to be the target signals, which will be sent to the main processor for further actions, instead of processing all the incoming signals continuously, which results in power wastage. Usually, not all the incoming signals will contain signals that are of interest to us. Such events of interest occur occasionally with low duty cycles, and only these target actions require the microcontroller's attention. So, a preliminary processing is performed initially. Granular decision-making module is a tiered wake-up circuitry with a sequence of screening classifiers in which all the unwanted signals are eliminated from the signal processing chain as and when they are encountered. In such cases, the microcontroller and the rest of the modules gets deactivated, thereby saving the power that would have otherwise been wasted on the non-target signals. This way, only useful sensor data gets extracted, which is made possible by the action recognition performed by the main signal processing chain. In the MSPC, filtering is performed initially on the input signals to remove noise, after which the signals indicating some user activity are segregated from those signals indicating that the patient is at rest. Certain specific signals are alone extracted based on specific features, thereby decreasing some dimensionality of the signal without affecting its information much. Following this, a series of processing blocks are used. In this, the incoming real-time signals are compared with predefined templates, and based on their similarities, the signals can be accepted or rejected, but the accepted ones alone will be sent to the main processor for further actions. The main aim of the screening classifiers is to distinguish the target signals from the non-target ones. To do this effectively, optimum bit resolution must be chosen. I've taken this graph from a paper for illustration purposes. This graph shows raw sensor readings indicating patient activities. Let's assume the rising from bending as our action of interest, and the other two actions, sit to stand and step backward, are taken as non-target ones. Now, let's assume two classifiers with 1 bit and 5 bit resolutions as shown in the middle and right graphs. This 1 bit resolution classifier can reject the sit to stand signal but not the step backward action, since this signal has the same value as the target signal. The non-rejected action can then be further processed by the next classifier in the chain, which is a 5 bit resolution classifier. Here, the step backward and rising from bending actions are distinguishable. Therefore, an incoming signal can be reliably classified as either target or non-target signals after passing through a sequence of low to high bit resolution classifiers. This consumes a lot less power than using all classifiers with full scale quantization as shown in the graph in the left side. Memory is the dominant source of both leakage and dynamic power consumption in low power embedded microprocessors. Here we will discuss 4 different mechanisms for reducing memory power. The first one is power gating. For applications with prolonged idle states in between bursty sets of incoming signals, the idle mode power consumption becomes significant. This can be greatly reduced by power gating, in which the current supply can be blocked for certain modules that are unused. The second one is using accelerators to speed up the execution time of tasks. Operations involving filtering, FFT, template matching, and certain computations can occupy significant number of clock cycles. This can be alleviated by using accelerators, which reduce the number of data memory accesses incurred for those computations. Third one is using instruction caches. Although microprocessors have small on-chip memories, since instruction fetching occurs frequently, an optimal cache configuration can be set up to speed up the fetching. Since the on-chip memories are already small, the caches must be designed to be of even lesser energy access than that of the on-chip memory so that some energy saving can be done. If the caches are of larger size, the hit rate might be high, but the cache access energy will surpass even the memory access energy, thereby defeating the purpose of caches. The last one is dividing memory into multiple banks. The memory banks that are idle are power gated so that the various transactions that accesses different memory banks can occur simultaneously. Memory banks of smaller sizes have lower access energy, but if the memory is split into banks of small sizes, it may result in too many banks, which in turn requires complex logic for selecting between banks, thereby ultimately resulting in high access energy. Splitting into larger banks, on the other hand, results in increased leakage power. So based on the expected average access rate of the memory, the bank configurations such as the size and the number of banks to be split up can be chosen optimally. Streaming the raw data directly to the external server through a wireless link might consume a lot of bandwidth, thereby wasting power. Instead, only the data that is needed can be extracted by performing on-node signal processing at various levels of abstraction. After extracting, only the useful data will be transmitted, thus decreasing the bandwidths of the wireless links through which the data will be passed, which in turn will enhance the energy efficiency. Bandwidth minimization can also be performed by initially compressing the physiological signals, transmitting it through the wireless link, and later reconstructing the signals back on the receiver end by using a compressed sensing decoder. Continuous signal acquisitions that demand large energy can be eliminated by using context-aware sensing methods, in which the physiological sensors can be activated and deactivated based on the monitoring requirements. This can be supported by the use of an inference engine that includes feature extraction procedure and pulse classifier. First, for the feature extraction procedure, the patient's pulse rate can be assumed to be the feature chosen. Now, pulse classification first takes place, and based on the patient's pulse results, it predicts the onset of a patient's exercise sequence, but it won't be able to determine when the patient stops exercising. For this, we need the motion classifier. If no patient activity was detected by the pulse classifier, then it doesn't proceed to the motion classification. Here, if the classifier indicates states like running or jogging, it shows that the patient is exercising and that his vitals need to be monitored. So, the ECG signal gets activated, and once the motion sensor indicates that the patient is done exercising, the ECG sensor can be deactivated. In addition to the aforementioned optimization methods, energy harvesting can also be incorporated in small autonomous sensors to convert ambient energy into electrical energy. This method of capturing and conserving energy serves as an inexhaustible substitute for batteries. These are some of the limitations that I observed. Although power gating mechanism can greatly reduce the power wastage during idle mode, its implementation exhibits some complications due to which it has not become a common ASIC technique yet. Powering off the logic block requires some planning in advance, as the logic might be needed even before some power restoration gets done. Unlike clock gating, gaining control over power gating cannot happen with ease. The second problem that I noticed was that although instruction caches and memory banks reduce power consumption, the act of combining both techniques in a single system could render them ineffective. Since caches reduce the main memory access rate, it ends up increasing the size of the memory banks from its optimal configuration, thereby leading to reduction in its energy savings. On the other hand, decreasing the access energy of the banks also decreases the cache size in an attempt to acquire low cache access energy. But due to this size reduction, the memory accesses satisfied by the cache also gets reduced, leading to cache misses. So far we have seen the different optimization techniques for reducing power consumption and various implications that different system architectures and circuit designs have on the power consumption and performance aspects of the wearable medical devices have also been examined through this presentation.